Now that we've worked on graphing quadratic functions, let's look at the next topic in the chapter. And this is finding maximum and minimum values of quadratic functions. Maximum and minimum values for quadratic functions will always occur at the vertex. And we really have two cases of our parabolas. When a is less than 0, the picture generically looks like this, and the vertex represents a maximum value of the function's graph. Conversely, when a is greater than 0, the parabola opens upward, and so the vertex represents a minimum value, or point on the graph. At the end, all we really need to do is use our vertex formula for any equation that's in general form. Where the maximum or minimum value will occur is the x value, which is minus b over 2a, and the actual maximum or minimum value itself will be that x value substituted into the function. So in essence, when we find maximum and minimum values of quadratic functions, it's essentially step 2 of our graphing procedure when we graph general form quadratic functions. Let's look at example 4 from page 353 of your textbook. And they give us a quadratic function in general form, f of x equals minus 3x squared plus 6x plus 13. And they ask, determine if it has a maximum or minimum value without graphing. And we don't have to graph it. Again, if we think about our graphing procedure, we know whether, by the leading coefficient, we'll know whether the parabola opens upward or downward. So in this case, a is minus 3, so a is less than 0, which means the parabola opens downward. And if the parabola opens downward, it's really going to look like this. So we know it's going to be a maximum value. Right, in part B, it says find the maximum and minimum value and where it occurs. Well, again, we just want to use the vertex formula. The maximum value will occur at x equals minus b over 2a. So using those values from our equation, right, b is 6, so we have minus 6, and then 2 times minus 3. Minus 6 divided by minus 6 is 1. Now that we know the x value, where the maximum value occurs, we are just going to substitute that value into f of x to find the actual maximum value. So we'll substitute x equals 1 into our equation, and eventually after evaluating, we come up with the value of minus 10. But remember, these are really the coordinates of the vertex, right? The vertex, if we were to plot it, would be at 1 minus 10. In part C, they ask us to identify the function's domain and range. Now, since we know the parabola opens downward, and we have found its vertex, what we can do is actually make a quick little sketch. It doesn't have to be perfect, but we know that the vertex would be at x equals 1, and then this y value of minus 10. And it'll look something like this. So this would be the point 1 minus 10. Now, the domain, of course, is going to be all real numbers from minus infinity to infinity on our x dimension. And our y dimension, well, what's the smallest y value? That would be minus infinity. What's the largest y value? Well, that really occurs here at the vertex, which would be minus 10. And of course, the vertex is included on the graph. With that point, we'll use a bracket. There is your domain and range. Now try pencil problem number 3. Now that we've learned how to find maximum and minimum values of quadratic functions, let's look at some applications. The first application will deal with motion in the path of objects when we have gravity. Remember, if we throw an object, whether it's a baseball or a football, or in this case the archer's arrow, the object is going to go up and then eventually come down. So objects generically will travel in a parabolic path that would look something like this. So notice this is a parabola that opens downward. So notice the model we have for the arrow does have a negative leading coefficient. So in part A of this problem, they say, what is the maximum height of the arrow and how far from its release does this occur? Well, again, just like what we saw in our previous example, we really just need to find the vertex here. So the first step in finding the vertex, let's find the x value where the maximum will occur. That'll be at minus b over 2a. Right? B is 2, a is minus 0.005, and we'll use that formula, evaluate carefully, and we'll get 200, in this case 200 feet. Now that we found where the maximum value occurs, we take that x value, substitute it into our function, right, and evaluate carefully. Remember your order of operations. Make sure you square the 200 first before you multiply by the minus 0.005. But if you calculate this correctly, you'll get 205 feet. So to answer part A of the problem, what is the maximum height of the arrow and how far from its release does this occur? Well, the maximum height will be 205 feet, and that will be at 200 feet downrange from where the arrow was released. In part B of the problem, they ask, find the horizontal distance the arrow travels before it hits the ground, round to the nearest foot. So what we really need to do is set this function equal to 0. Remember, f of x models the height of the arrow. When it hits the ground, the height will be 0. Now, because of this model here, in the decimals you see, we can't factor this to solve this quadratic equation. We'll have to use the quadratic formula. So remember, before you use the quadratic formula, carefully identify a, b, and c before you get started. So we'll use the quadratic formula and substitute our values of a, b, and c into the formula. So again, I recommend set up the formula correctly and be very careful. I would always start with the radical term here when you're using your calculator. And notice I see a minus times a minus will be a plus. So I can do 2 squared plus then multiply these values together. I would get a value underneath the radical and then finally take the square root, as you see here, 2.02. So be careful with the quadratic formula in your calculator. Break it down one piece at a time. And then eventually, when you calculate your 2 roots, you'll get x is approximately minus 2 and 402. Now, of course, the 402 is the real answer that we're looking for here, not the negative. So the other root can be ignored. And so to answer part B of the problem, we know the arrow hits the ground at 402 feet downrange. In part C of the problem, they ask us to graph the function that models the arrow's parabolic path. So when we put all the pieces together, this is what it'll look like. First, our y-axis is really the height of the arrow, and x is the distance downrange. And actually, where we start is the y-intercept. If you look at the function carefully, when x is 0, the function value is 5. So that's really telling us the arrow is released from about 5 feet above the ground. There's our vertex at 200 and 205. And then there's our x-intercept of 402. So in any application problem, see if your answers make sense. Notice, if the parabola is essentially symmetrical, then if it reaches its maximum height at 200, a value around 400 makes sense. The fact that it's not exactly 400 is because the arrow is not starting off the ground at 0 exactly. It's off the ground a little bit at 5 feet. But again, this answer 402 looks very reasonable since 200 is halfway where the arrow reaches its maximum height. Let's look at another example of looking for maximum and minimum values involving quadratic functions. In example 6, on page 357 of your text, we'll see this example minimizing a product. So among all pairs of numbers whose difference is 10, find a pair whose product is as small as possible. What is the minimum product? Sometimes these problems are referred to as optimization problems. In optimization problems, there's really usually 2 pieces we see in the problems. One is sometimes what they call the objective function, a quantity to be maximized or minimized. In this case, we want to minimize our product of these 2 numbers, x, y. The second piece you can see in optimization problems is something called the constraint. It's a restriction on the value of the variables. And in this case, our constraint or restriction is the difference between these 2 numbers, x and y, has to be 10. Now, what we could do is use this constraint equation to solve in terms of one variable. In this case, I'll add y to each side and subtract 10 to say y equals x minus 10, because what we need to do is put our objective function here in terms of one variable. So notice now that I have this expression for y, I'll substitute that expression, and now our product is x times x minus 10. And that's going to be a quadratic equation. So now I can rewrite that expression as x squared minus 10x. So I'm going to identify A and B because we know that the minimum value is going to occur at x equals minus b over 2a. So we can do that calculation. Minus 10 divided by 2. We get 10 divided by 2 is 5. And so what's the minimum value? Well, that'll be the function f evaluated at that value 5. Now, due to our restriction, right, if x is 5, then y is 5. But if we wanted to use this function in one variable, okay, if x is 5, we'd get 5 there. And then 5 minus 10 would be minus 5. That product would be minus 25. So just to summarize, right, we found x was 5. If we use this constraint equation here, well, 5 minus 10 is minus 5. Of course, that product will be minus 25. Now, do pencil problem number 4. Let's look at it. One last geometric example of an optimization problem. And this is example 7 on page 358. And this is maximizing the area. If you have 100 yards of fencing to enclose a rectangular region, find the dimensions of the rectangle that maximize the enclosed area. So remember, if you have a rectangle, its area is defined as x times y. This is what we want to maximize, and its perimeter is 2x plus 2y. So the information we get from the problem is that we only have 100 yards of fencing to put on the perimeter. So if I set our perimeter formula equal to 100 and then solve for y, eventually I'll get this expression, y equals 50x. And just as we saw in the previous problem, I need our area function to be in one variable. So where I see y there, I'm going to substitute 50 minus x. And this is really the quadratic function that we want to maximize. Now that we have the quadratic function, right, we know the maximum occurs at x equals minus b over 2a. Remember, we're just using the vertex formula here. So a is minus 1, b is 50. Right, we substitute those values into the expression, we'll get 25. So we know that the max occurs when x is 25 yards, and using this equation for y, we can of course find the y value, 50 minus 25 is 25 yards. So to finish the problem, they ask, well, what is the maximum area? So if we use that original formula for our area, x times y, well, x and y are the same, they're both 25 yards. That'll give us a maximum area of 625 yards, and the dimensions are actually a square of 25 yards by 25 yards.